In this slide, we're going to see the transformation T in the B basis. In the last few slides, we have shown that the transformation TB transformation in the B basis is equals to D if A represents PD P minus 1. Now, why is this so? Well, we have seen in the last slides that x in the standard basis pre-multiplying by P minus 1 gives us x in the B basis. We then pre-multiply by D. That means D is acting on x of B in the B basis. And then the last step is, which is YB, converting back to the standard basis by pre-multiplying by Y. When we see these pictorial representations, so what we are basically doing is that we are tracing this path, which is x going through P minus 1, going through D, and then going up again through P. What we see is that we see these three operations acting on x, and we concluded that these three operations which represent x actually means that we have just converted x into the B basis using D to act on the x in the B basis and then converting it back to the standard basis. So that was what we did. Now, Ley have another way to represent this this transformation in the B basis. Alright, he says that the definition of a T in the B basis can be done in this way. Basically, he gives you a matrix, and this matrix is the transformation on each of these B. And what is B? B is the P matrix, the columns of the P matrix. And we have to transform this B column by column and then change it into the B basis. So it is a transformation of the columns of P and then converting them into the B basis. Alright, let us see why it is equivalent. TB is equals to D. That's the conclusion. Why is this so? Well, we already know from our previous example that this is true, but why is Ley's representation also true? Right, now T in the standard basis is represented by A. So T of B1 is simply A of B1. So all the columns of B1 to Bn, which are the columns of P, the eigenvectors, are transformed by matrix A. A times B1, A times B2, until A times Bn. Now there's a change of basis needed here because A times B1 is still in the standard basis. Right, so how do we change something in the standard basis to the B basis? Remember, all we need to do is to pre-multiply by the change of coordinate matrix is inverse. So it's P minus 1 times AB. So what happened is that in the first column, it was AB1 in the B basis, and this is realized by P minus 1 AB1 for the first column. And in the last column is AB1, sorry, is ABN in the B basis, and this also means that it is P minus 1 ABN. Right, so we can see that P minus 1 is common, we can see that A is common, we can bring it out, leaving with us a matrix containing B1 to Bn. But this is the definition of P. So what happened? What we have is P minus 1 A times P is the transformation in the B basis. Now, remember we told you that transformation in the B basis is D, but now we have P minus 1 AP, P minus 1 AP. Remember that A is equals to PD P minus 1. Therefore, we substitute this into here. So it's P minus 1 P D P minus 1 P. P minus 1 P cancels, P minus 1 P cancels, leaving us with D is the transformation in the B basis. So this is Ley representing transformation in the B basis through this definition of TB. It's very different from what we have done, but I guess you can, whichever is simpler to you, you can just use it to find the transformation in the different bases. Thank you.